So now here in this session we are going to deal about what is an angular velocity is. Here in this session we are going to deal what is an angular velocity is. So as you see on screen, so the fluid element is being considered and a three-dimensional fluid element is being considered. So here on the three-dimensional fluid element at a time t1, to t2, the same element is taken at the time t1 and at the same element at the time 2 when it is being taken. Here you just see the fluid element has not retained its shape as like at the time t1, but when it has reached to the time t2, when it has reached from t1 to t2, it has been changed its shape. Maybe because of this requirement of that particular fluid flow to transfer from one position to the another position, or whatever may be the fluid requirement or the geometry available in this one. In order to discuss about this particular fluid motion, so we have to say that generally the fluid would be, so generally the fluid motion would be like, so may not be the same at the instant of initial time of t naught to the time of t naught plus delta t. Now the question comes, so what do you exactly mean in this one? So at the time t and t naught, so that means whenever the fluid is allowed to move, whenever the fluid is allowed to move whenever the fluid is allowed to move from one position to the other position, so the fluid may be going for the different type of transformations in that one. So that may be the fluid may be just translating like this. So here on screen you can see where I'm annotating it here in this one. The fluid is just translated from its initial position to the final position in order to reach to the next point. Or it may undergo with a linear deformation, or it may undergo rotation, or it may undergo angular deformation. So that is when you are talking about the fluid flow. When you are talking about the fluid flow movement, it can be translation, it can be linear deformation, or it can be rotation, or it can be angular deformation, or it is a sum of all this also may be available in that particular fluid flow. Or it may be sum of all this particular also. Whenever we are taking that particular fluid flow as general motion of the fluid flow is being considered, it may undergo translation. So that means one position to the other position without changing its shape, only the coordinates of it is being, so that means the shift of the axis has been made. When you are talking about it is translation. When you are saying it is a linear deformation, so that means the initial fluid element which was given within a dark line has been deformed and has got the new dimensions in it. So that we will call it as a linear deformation, where it is being stretched onto the x-axis, where it is being stretched onto the y-axis. And when you're talking about the rotation, here in this rotation, so there is no translation or there is no deformation happened, but the fluid has taken a angular velocity change. There is a fluid which has changed with an angle. So let us take some angles as theta 1 and theta 2. So that is the theta has been changed. That means the fluid is going about to rotate about its axis. So that generally we'll call it as a rotational axis or rotation about the fluid element. Or it may go for the angular deformation also. The fluid element may go for the angular deformation also. Here also you can see that the angular deformation is made, but it is not a pure rotation. It is not a pure rotation, whereas in the fourth number if you see, so there is an angular deformation. So that means it is not simply rotated, but it has made even the angular deformation where the angle theta 1 and theta 2 both are made in this one. So that is the case possible with respect to the fluid flow. When you're talking about the fluid flow movement or the general motion of the fluid flow, can be translation, can be linear deformation, can be rotation, or can be angular deformation even. So as how do we predict this one is based upon the type of fluid flow we are discussing about, in order to discuss about, or in order to detail about the behavior of the fluid flow, so the general motion of the fluid flow should be aware to the individual in order to state whether the fluid is going for only translation, in order to state that the fluid is going for only linear deformation or only rotation or only angular deformation, or in a general motion of the fluid flow. This may be possible with all four types, right? So now So as how do we predict this one means we will place a streamline along this particular fluid flow, and based upon that particular streamline behavior, so that is whereas the streamline definition is dv by dt. So at any point along the fluid flow, if you are tracing that velocity, so that velocity is exactly defined the tangential point of the curvature of the particular fluid flow which is making. So based upon this one, so we can state that whether the fluid is going for the translation, linear deformation, or rotation, or angular deformation. So that according to state that behavior of the fluid flow, this is required for us. This is required for us in order to discuss about what exactly the fluid motion would be happening in that particular fluid flow. In that particular fluid flow. So here, how do we state that this is fluid is going for the angular deformation? So the fluid flow may be going for the angular deformation. That can be when you're going for the angular deformation, that we'll say that the fluid element has been distorted. The fluid element has distorted. So that has not remained with its original dimensions. That has not remained with its original dimensions. So the dimensions of the fluid flow has been changed in that case. So that is a different types of fluid flow motions possible in case of a fluid flow. Now let us discuss about that in detail. So here my interest is about the angular deformation. My interest is about the angular deformation of a fluid flow. Angular deformation of the fluid flow. In order to discuss about the angular deformation of the fluid flow, so what I have considered is I have considered at a point P. I have considered a point where my u velocity. So where my u velocity and v velocity is defined on an axis of x and y. On an axis of x and y, where my u and v velocities are being defined initially. So where my u and v velocities are being defined initially. So let me take it separately and annotate it here. So I have taken okay, sorry. So what did we have taken? So we have taken a fluid element. We have taken a fluid element at a time instant of t, in order to discuss about the rotation or the angular velocity of the fluid element, in order to discuss about the rotation and the distortion of the fluid element. That is the fourth case directly I'm dealing with. So in order to discuss about this one, so what we have done is, so we have taken one fluid element. So where the initial at this point the velocity along this particular direction, so this is the x direction and this is the y direction we have considered it. So at this point u, so let me take in this direction whatever the velocity it is traveling, I have taken it in the x direction, it is u, and along the y direction it is v, along the y direction it is v, sorry I have written it as y. So along the y direction it is v on this one. Now you just see this fluid element along this particular axis, it is being separated by a distance of, it has been separated by a distance of dy. It has been separated by a distance of dy, and along the x-axis it has been separated by a distance of, let me take this distance, the elemental distance which has been separated on that one. So let me take that distance separated on this x-axis and y-axis as dx and the dy. Dx and this is dx, and along the y-axis, let me take that elemental distance of this particular fluid element as dy. Dx and dy are the particular fluid elements which we are talking about. So that is being separated by distance of. So that means the fluid element is having, let me name this fluid element as A, B, C, and D. Now if you see, so whereas the velocity available at a point A, so that is initially started with the velocity of u. Initially it has started with the velocity of u, and when I'm moving to the other side of it, so where AC and BD are parallel to each other, where AC and BD are parallel to each other, so that is both the horizontal surfaces are parallel to each other, and where AB parallel to CD, where AB is parallel to CD. So these two axes are parallel to each other. So that is these two, that means CD is parallel to AB and AC is parallel to BD. Now when I'm talking about the velocity available, at a point A, and moving on to the point B. So there may be some velocity gain or velocity change which is happening on that particular fluid flow. So that I am representing it as dou u by dou y, into dy. So if you take the mathematical expression again of this one, so it will remain same. Similarly, when I'm talking about the v velocity at the point A and at the point C, when I'm talking about the velocity which is acting in the parallel direction, so that is along this particular direction, that can be written as v plus dou v by dou x into dx, dou v by dou x into dx. So that is at the point C, that is at the point P parallel to that particular point. So I'm not sure what is the velocity available at this point C, so I have written it as v plus dou v by dx. So that is a change possible, there is a change possible after it moving a distance of dx, after it is moved in a distance. So that is the reason I have kept the denominator in the dx, and this is possible with a velocity change when it has moved out, separated by a distance of dy. So that is the reason that's a dou y and dou x, so that is being separated by this particular distance. So I'm not sure what is the velocity change happening in this one. So for that one I've represented with a mathematical way, so that is u plus dou u by dou y into dy, plus that is u is being changed by this particular distance of dy. So, and this is acting at a distance of dy, so that is being represented on this one, and v acting along this particular axis, so that is v plus dou v by dou x into dx. So these are all the velocity component changes which is happening at a time t. So at a time t they have just initiated that velocity. So at a time t they have just initiated that velocity. So now this is at the instance of t is equal to, let me take the t is equal to t instance. So that is at the instance of t is equal to t or t is equal to t naught. This is at this particular instance where they have started the velocity points at the initial point A and C, where it has started with a B. A point, the initial velocities have been started with along the x and the y direction, that is u and v, and at the point B it has started with the velocity, and at the C it has been parallel to this particular point. So where I'm considering, so that is u parallel point and the v parallel point I've considered it, and here in this, if you see, the velocity points have been given at the point B and at the point C. So that was at the initial point where it has been changed with respect to some velocity. So that is u plus dou u by dou y into dy, plus, and along the y direction if you see, so that is v plus dou v by dou x into dx, right? V plus dou v by dou x. So now let us see when it is happening, or when it is with respect to changing with respect to the time t, when it is changing with respect to the time t. So what happens to this particular fluid element? Let us see. Now if you see this particular fluid element, when it is being applied with a u and v velocity after a time t, just see after the time t, where initially we have considered that it was with a velocity of time. So it was the initial time where it was a t is equal to t. So it was initially t is equal to t. Now the velocity has been changed with respect to the time. So so the velocity has been changed, that is t plus delta t. At an instant of t plus delta t, what has happened is, because of the change in the velocity happening from the initial point of A. So the initial point of A has been written at the point A only. But because of the increment at this particular point C, because of the increment at this velocity of point C, the fluid element started rotating in this direction, and because of this particular velocity, because of the velocity change happened at this particular point B, the fluid element started changing the velocity, started changing that particular fluid. So that means the fluid has undergone the deformation. The fluid has undergone the deformation after certain time. So that we have written it as t is equal to, now at this instant, t plus delta t. So that means after certain time t, the fluid element, so one fluid element where it is acting at this particular point C, it is going in the anti-clockwise direction, and at the point B it is going in the clockwise direction. So where the fluid element has completely deformed. If you see after time t plus delta t, the fluid element has completely got deformed at this point. Now, so in that when we concentrate how much the deformation has happened on that particular fluid element, well, let us see. So in order to discuss about that one, first we should see that, so the initial point was at C here, and the initial point of B was at here, right? So but this has been changed due to that velocity change happened on that one. Now my interest is how much is the velocity change happened in this one. How much is the velocity change happened in this one? So let us check that velocity. So when I'm talking about the velocity available on the other side, as from the initial point to the final point, so that is final point u plus dou u by dou y into dy minus u. This is the velocity change applied at this particular point P. And where is that where we are talking about the point C? So that is after time t plus delta t. So what is the velocity change happened is because of this. So this is final point. So that is v plus dou v by dou x into dx minus v. So minus v. So that means my resultant velocity available on this, my resultant velocity available at the point B. So that is so from this resultant, so when I'm subtracting, so the u and u got cancelled. So that is, so then I'm written with the value of, so that is dou u by dou y into dy into delta t. So here if you see after time t, after time delta t, so this is what the resultant variation we got it. This is what the resultant variation we got it in this one. Now you, my questions are, how did you get this delta t multiplied on this term? How did you get the delta t term multiplied on this one? Okay, so don't just wait, just hold your doubts. I'll clear that doubt. So but up to this one, you just be clear about this point, so that it is giving the velocity at this instant, that is dou u by dou y into dy into delta t. So that I'll clarify it, right? So here if we see whatever the change in the velocity is applied at this particular instance at the point C, and because of this change, the fluid element has got distorted in this direction. The fluid element got distorted in this direction, and completely the fluid has become a trapezoidal. The fluid has become a trapezoidal in shape after time instance of t plus delta t. Now my interest, so I'm interested to know about how this particular fluid element has changed it, its particular how now we are sure that, so because of the velocity applied, that the fluid element has been influenced with some additional velocity at this point B and at the point C. Okay, because of that one it has been changed. Now why did we multiply with a delta t with this equation? Why did we multiply with the delta t in this one? So that is a doubt you're holding, might be right. So I'll clear about that even. So but let me clear this notions first. So now if you see now, so if because of that particular fluid element there is an angle made, so have represented, so as far as this clockwise direction it is being, as far as the fluid element is being considered, so the fluid element has been reduced in this particular direction when it is being applied. So that reduction I have represented with the minus delta theta 1, or you may say that it is clockwise direction, so that is being given as a negative sign, and the anti-clockwise direction that is given in the positive side. Now how do I obtain this theta 1 and theta 2? So how do I obtain this theta 1 and theta 2? Because that the change happened from an initial fluid element to the final fluid element. It has changed with respect to the time. So that is t plus delta t. That is with respect to the t plus delta t. In order to address that one, let me take an angle where it can address theta adjacent angle and theta opposite angle. This is only two references I have in this one. So that means the theta adjacent one and theta opposite side. So let me take that as tan of, so because tan of theta only it can adjust with the opposite side by the adjacent. So tan of minus delta theta 1, it is the angular rotation. So this is an angular rotation, that is a theta instance per time. So that is a theta instance per time. So we can write it as, so what are the angular rotations? That is opposite side by, so that is opposite side, it is dou u by, so I am writing it for the theta 1. So that is, sorry, theta is opposite side, yes, correct, dou u by dou y into dy into delta t divided by dy. And similarly when I'm writing about the theta 2, so that is minus tan of, sorry, that is plus delta, so this is plus tan of delta theta 2 is equal to, so that is opposite side, that is dou v by dou x into dx into delta t divided by dx. So from this I get my resultant of, if if my angle is very small, if the angle is, if the theta is small, if the theta is small, so my delta theta 1 will become minus of that is sorry dou u by dou y into delta t. Here my delta theta 2 will become, here my delta theta 2 will become dou v by dou x into delta t. Now still you might be not clear about what exactly this time instant is there. This time instant, why the delta t has been multiplied here in this one. So here, see here, so what exactly we are interested in this one is, so why the delta t is multiplied? Maybe you are still asking about that question only. So if you see what exactly the velocity definition is, what is the velocity definition? Is the velocity definition is distance
Displacement.
by time. So the velocity distance is, the velocity definition is distance by the time. Now when I'm talking about this vertical height, when I'm talking about this vertical height, when I keep it with respect to the time, so when I keep it with respect to the time, so that means that at every instant of the velocity change, my distance is varying along that one. So in my vertical direction or the vertical distance when I'm taking it, so I have what I have in order to balance this distance by the time of the velocity, because at this point of instance C I have got it as velocity distance by time. So my distance moved along this one is actually, distance moved along that one is actually dou v by dou x into dx. Distance moved on that one, that I got to know. So that is dou v by dou x into dx. But whereas the dx, dou x, dou by dou x and dx, that the differential term and the partial differential terms will get cancelled. But I am retained with the velocity only. My interest is to obtain the distance on that one in order to substitute at this particular angle. So that is distance by the time. So in order to balance that equation there, I have multiplied with a delta t. I have multiplied with a delta t. So that is the reason why I got the delta t in that one. So that means here that is stating about the distance available here. dy got cancelled, and delta theta 1 I got it as dou u by dou y into delta t, and delta theta 2 I got it as dou v by dou x into delta theta. This is what I have got it in the two terms of the angle made on this one, right? Angle made on this particular equation. So that is delta theta 1 and delta theta 2. Why this delta, why we have not considered it as tan of delta theta, as the theta is very small, as the theta, so that means the angular rotations what is made by the fluid element, if it is very small, the tan of theta 1 can be approximated with directly as theta 1 in order to counter, because we have taken only small elemental one, so that elemental changes which is happening, so has been approximated it as, that has just been approximated, that is equivalent to the theta, So now let us see what exactly the angular deformation is being defined as. Well, let us see what exactly the angular deformation is being defined as. Now let us move on. What is the angular velocity is defined as? What is the angular velocity is defined as? Angular velocity is defined as, it is the average of the, angular velocity is defined as it is average of the rotations made along, that is the, it is the angular theta is that is angular rotation, along the whichever the plane we are considering it. So that means currently we are considering the xy plane. Currently when you are considering the xy plane, so that means the angular rotations whatever being considered along this particular plane are given by average of the angles made, that is average of the angles made along that particular direction. So that is delta theta 1 plus delta theta 2. So delta theta 1 plus the delta 2. Now the question comes, where exactly this average angle rotations I can see, where exactly, in which one, along which axis I can make this angular rotation I can see. So where, if you see, so this two, so the plane of xy is perpendicular, so where, if I am pointing my pen to you, so when I am pointing my digital pen to you, so that means this is the angle where about the rotation is happening, so this is about the z axis, so let me represent that the angular rotation is given by the WZ. Let me take that it has been, the angular rotation is along the z axis is being represented by the WZ. The angular rotation is actually the average of the angles made in between that two. So the average is, so this is by utilizing the definition. I'm just utilizing the definition. So that is along that particular plane perpendicular to that only I can see that the angular rotation made in this one. right? So that is being defined as omega w, omega z is equal to half of delta theta 1 plus delta theta 2. Right, so half of delta theta 1 plus delta 2. So this is what the angular rotations we have made on this particular plane of x, y. So that means the rotation is happening. The rotation is happening about the plane which is perpendicular to this one. Then only. So if you are not sure about still, so you just take a paper to the pin your paper to the pen needle, the pen nib, and start rotating your pen and start rotating your pen. So your paper also, if it is stick to that one, your paper also makes an angular rotation. That is what I am talking about. The angular rotation made on that particular fluid element. So that means here we have considered only the two dimensions. So that is the angular rotation about which is happening along the z axis is the average of delta theta 1 plus delta theta 2 is a delta theta 1 plus delta 2, or it may be from your definition. So you might be stating, sir, I have heard of the definition is that the angular rotation varies with respect to the time, or it may be c into the r, right? So the angular rotation, so that is the angle at that particular instant, c into the r, right? So even in that way also when you are writing, so you will be obtaining your derivation and finally the conclusion will reach at to this particular point only. Now substituting substituting the values of the theta 1 and theta 2 from the derivation we have made or from the previous slide, we what we have obtained here in this one is that delta theta 1 is equal to minus do u, so I'm just writing it from here, so minus do u by do y into delta t plus do v by do x into delta t. So but I told the angular rotation is nothing but the angle with respect to the time it has to be considered. So that is d theta by dt. So that is d theta by dt. So from that, when you're considering about this delta theta 1 by delta t, so my expression for the omega z will become, so do v by do x minus do u by do y. This is the rotations which is happening along the, which is happening in the plane of xy, but about an axis of z, This is along which plane means this is about the plane of z. We have obtained this rotation. Now similarly when we are approaching into the other axis, so that is omega y and omega x. We will obtain that as omega y and omega x. Okay. So that is omega y and omega x, we will be obtaining that solution. So when you are rotating about the other axis, so that means every time it may not be possible to rotate only the xy axis. So I want to rotate about the y axis, I want to rotate about the z axis, I want to rotate about the x axis. So similarly you can write even in the other axis frames also, so that gives you a complete solution, in about three-dimensional frame. So let me write first the generalized equation for it. The angular rotation about the three axis, that is j plus omega z into k. This is the actual equation for the angular rotation of the fluid element for a three-dimensional fluid element. Angular rotation for a fluid element in three dimensions, or angular rotation, the fluid element is happening in the all three dimensions. So what we can write along this particular one, so that is about the z, we have written it. So then let us write it about the y and x in a similar format. Then you will get the resultant solution for this particular angular velocity which is happening on this particular plane along the z axis. So that means at a time it is about the one axis we have been considered here in this one. So when it is happening along the three axes, so this is what the resultant solution we will be getting it about the three-directional frame element. So when we are talking about the three-dimensional frame element, so that means the omega is actually the summation of, so that is omega I plus omega j plus, so that is x, y, and omega z into k. So that we will get it as So that means the x component. So just we have done with a z component. So when you are doing similarly along the y component, you will be getting the resultant equation of this. And when you are doing about the x axis, you will get the resultant axis about this one. So that is rotation about the x axis, rotation about the y axis. So this is your omega x, omega y, and omega z. This is a rotation about a three-dimensional frame. This is the rotations happening about the three-dimensional fluid element when it has been considered. So this is what the actual derivation of the angular velocity, actual derivation for the angular velocity which is happening in the three-dimensional frame. So when you are talking about the three-dimensional frame. Now so when the tips are being considered, so when you are talking about, sir, here in this particular one, in the classroom discussion or whenever we are going for the regular session, so this would be the derivation we would be doing it. It is for given for the long answer question. It is given for the long answer question, or when it is given for only equation to be asked. Now when I'm going for the competitive exams, I may not have such time to obtain this solution, complete solution. I may not concentrate on the time to be given for the complete time to in order to obtain the solution. So in that case, you tell me, how do I remember in case of competitive exams, if I have been asked to, if I have been asked to obtain the solution for this one, or if I have to use the solution only, in that case you can use a simple hint that when it is rotation is about the x, so that means you don't find any components related to the u and v in that axis, in that rotation which is happening. And the other one which is being is, so we have to follow u, v and w. So these rotations we have to follow, so u, next it is w, then it is v, then it is, so this rotation when you follow it, so when I'm talking about this axis rotation about the x, so that means initially I have started with the w, the next it is going to be v, and under this term it is exactly going to be, so that is the opposite to this one. So that is the y component will be available, and here the z component will be available. And similarly when you are talking about the y, so that means the v and the y will not be available in that one. So here this, if you see about the y component of it, so where the next rotation, so that means first one it has to rotate with a clockwise rotation. So where first term would be v, u positive, and then next w would come. And when you're talking about the third one, so that is when you're talking about the z, so that is first term would be v and second term would be u. And this is only for the competitive one, I'm telling you, this is only for the competitive, those who are going for the competitive exams and where the fluid mechanics is being given a proper weightage. In that one you can best utilize this way in order to address your equation or the solution in a single minute or less than a minute. You can write that equation of the angular deformation or angular velocity or the angular deformation happening in this one, and this opposite elements or opposite components of the velocity would be available in this one. So this is how, when you easily verify it in order to satisfy your equation whether it is going for the angular rotation or not, this can be best utilized when you are going for the competitive exams point of view. As far as your regular classroom sessions are being considered, they might be asking you to derive the complete angular velocity derivations, but whereas a competitive one, we don't have enough time. Within a few seconds we have to obtain the solution for it. So this is the best way. How do I write that solution? Less than a minute. This is a hint you can utilize it for competitive one. This is the best way you can utilize it